Hey everyone, and welcome back to another studio review video. So this is going to conclude our three-part electrical engineering series that we started with Studio 7. So today we'll be covering all the content involved in Studio 9. So basically, just to go over today's learning objectives, we're going to cover some semiconductor device physics, and then we're going to circle back to our digital logic and digital circuits content that we started in Studio 8. And then we'll also do some example problems where we make some circuits using what we've learned and the different components we've learned. And we'll do that using a software called Logisim, which I'll show you all how to use. It's actually pretty easy to use. Okay, so let's go ahead and jump into this because there is a lot of content that we need to cover today. So today we're gonna start with semiconductors and explaining how transistors actually physically operate. So a quick recap before we sort of dive into that. Quick recap of the sort of rules that we laid out last week. So last week for the NMOS and PMOS devices, which are the two main transistor types we'll talk about in this studio, I just sort of said, okay, we're just gonna lay out these rules and I'll explain them in Studio 9. So here are the rules, just a quick recap of those. So basically we said that PMOS devices turn on when a logic low is applied to the gate and they turn off when a logic high is applied to the gate. We also said for PMOS devices that they're better at passing a logic level high. Okay? Now, NMOS devices are sort of the opposite. NMOS devices pass current when a logic high is applied to the gate, and they're better at passing logic level lows between the drain and the source. So those are the sort of rules that I said to just take for granted in Studio 8. Okay, so the first concept that we really need to go over today before we can really dive into NMOS and PMOS device structure is this concept of doping. So before I talk about that, what I want to describe is this intrinsic silicon structure. So what does silicon look like? And silicon is what we're going to use to make all these transistors. We could also use some other semiconductor material, but since silicon is the most common material used to create semiconductor devices like transistors, I'm going to stick with that material for now. So back to this discussion of intrinsic silicon. What is that? What does it mean? What does the crystal structure of silicon look like? So silicon, before we add any doping to it, before we add any impurities, it forms this diamond cubic crystal lattice structure. And I'm not going to go into different crystal lattice structures, but basically what you need to know for the purposes of understanding this concept is just basically the silicon has 4 atoms in its valence band. Or I'm sorry, not 4 atoms, but 4 electrons in its valence band. Now to be stable, it wants to have 8. And because of this diamond cubic crystal structure that it arranges itself in, it has, each silicon atom has 4 neighbors, silicon atom neighbors. And so each of those atoms has 4 valence electrons. So I'll just draw those in blue here so that you can see them visually. And so what's going to happen, as you might imagine, so we want to have 8 electrons in the valence band. So this silicon atom in the middle is basically going to create covalent bonds with each of its neighbors. And so now it effectively has 8 electrons in its valence band. And every other silicon atom is going to do the same with its corresponding neighbors, and we'll reach this state of stability where the intrinsic carrier concentration is equal to the electron concentration and is equal to the hole concentration. And so what I'm really saying is that we have an equal number of charge carriers. So basically, to sum this up, I'm saying that Ni, which is the intrinsic number of charge carriers, or the intrinsic charge carrier concentration, is equal to the electron concentration, and that's equal to the hole concentration. So I think we all know what electrons are, but if you don't know what holes are basically just the absence of electrons. So what we're saying here is simply that we have the same number of electrons in holes, so we have this state of stability. Okay? So that's for intrinsic silicon. Now, the idea with doping is basically that we can replace one of these silicon atoms, or a few of these silicon atoms, with some other material. So let's say that we get rid of this middle silicon atom and replace this with an atom like phosphorus. So now we're going to put phosphorus in here. Well, phosphorus instead of having 4 valence electrons like silicon, phosphorus has 5. And so it's still going to form these 4 covalent bonds with each of these silicon neighbors, but we end up with this extra electron. So now, because of the way that we've doped this, we have an abundance of electrons. We call this N-type doping. So N-type doping is when we have more electrons than we have holes. So electrons will denote with N, and P's will denote with, and holes will denote with P. Okay, so now another way to do this is to inject a material that has less electrons than silicon. So if we inject something like phosphorus, we end up with more electrons, but we could also put something like boron. And in the case of boron, we end up with 3 electrons in that valence band. And so we're left with a hole here. And this is for boron. So in this case, we end up with an abundance of holes, or in other words, a lack of electrons. So we have a hole here with boron, and this is basically going to be P-type doping. And in P-type doping, we have more holes than we have electrons. So that, in essence, is what doping is. And now, one final note that I want to make here is that in all cases, the intrinsic carrier concentration squared, so that's N sub I squared, so N sub I is the intrinsic carrier concentration, is equal to the concentration of holes, or the concentration of electrons times the concentration of holes. Okay, so this is a very important relationship that allows us to understand what's happening when we dope silicon with a certain density of donor or acceptor atoms. So donor atoms would be things like phosphorus that have extra electrons, and acceptor atoms would be things like boron that have extra holes or a lack of electrons. So they tend to accept electrons, right? Because they have holes. Okay, so just to make that point concrete, let's say, so we have some intrinsic semiconductor material like silicon. Let's say we have that material is doped with a density given by N sub D. So we'll say some density of donor atoms per unit volume. So we'll say for this example, per centimeter cubed. This is just an example, right? Okay, so in this case, we are basically given the number of, or the density of electrons. So the density of electrons is going to be roughly equal to that density of donor atoms that we were given. And so using that equation that I just introduced, we can sort of approximate the number of holes that we have, or the density of holes that we have. So that'll be given by Ni squared over capital N sub D. And in this case, we have more electrons than we have holes, and so electrons are called the majority carrier in this case. So this is the majority carrier, and the holes will be the minority carrier. So now, in a similar way, we could also say that we dope some intrinsic silicon material with a density of capital N sub A acceptor atoms. Per unit volume. In this case, we'll stick with cubic centimeters. And so in that case, we are essentially given an approximation for the concentration or density of holes. So we'll say P is equal to N sub A, and we'll use our equation to get an idea of the number of electrons. So in this case, we have more holes than we have electrons, so the holes will be the majority carrier, and the electrons will be the minority carrier. So this is maybe a little bit simplified, but in essence, this is what doping is. Okay, so now that we understand how doping works, let's talk about the actual structure of these MOSFET devices. So this is the core of what we want to talk about with our little semiconductor topic here, okay? So on this slide, you can see an NMOS device. So we're gonna go over NMOS first, and then I'll talk about PMOS. So basically, let me just start redrawing this out, but this is what the device looks like. So what we've got is we've got these two wells that are doped N+. So N+ just means they're doped really heavily N-type. So they have an abundance of electrons, of extra electrons. And then we've got this lightly doped P-type substrate. So they're embedded in this big, lightly doped P-type substrate, which we refer to as the body. Okay? And now between these two wells, we have some sort of insulative material. A lot of times this might be something like silicon dioxide, whatever the case may be, just some insulative material. But silicon dioxide is a pretty common one, so I'm gonna write that. And then we'll have a conductive plate on top of our insulator. Okay? And that conductive plate is going to be our gate. So this is our gate. All right, so let me move this guy down. And now we just need to identify what the source and what the drain is. So this is a symmetric device. It doesn't actually matter which well we call the source and which one we call the drain. So I'm just going to choose this one to be the source and this well to be the drain. All right. And also an important note, we always connect this P-type body to the source. So there is an electrical connection connecting that P-type substrate to the source. Okay, so now for the purposes of this example, I'm going to say that the source is at ground. So this will just make everything a little easier to understand. But just know you could connect a variety of things to the source. Just for the purposes of this explanation, I'm going to say that the source is at ground, okay? All right, so first things first. Remember we said, so this is an NMOS device. So this is NMOS. And remember we said that NMOS devices turn on when we apply a logic high to the gate. Well, it turns out that there is some voltage, some positive voltage, because it is a logical high. There is some positive voltage at which this device turns on. We call that voltage the threshold voltage. So in order for the device to turn on, we need the voltage between the gate and the source. So we say VGS, that is denoting the voltage between the gate and the source. So that would be VG minus VS. So this is the voltage at the gate and that's the voltage at the source. So that's what VGS is. I'm gonna erase this though. So just keep that in mind though. So we say VGS needs to be greater than V threshold. And I'm gonna say V threshold N to denote this is the threshold for an NMOS device. So if that is true, then the device will be on. So let's just say for the purposes of this example, we'll say, and that turns it on. So we'll say that VTHN is 0.7. Just a number that I chose. It could be a variety of other things. This is just dependent on the particular device that you're working with. And you just check the data sheet or whatever to figure out what VTH actually is. So let's just say for this example, VTHN is 0.7. So if that's the case, then our gate needs to be above 0.7 for the device to turn on. So let's just say that our gate is at 1.7 volts. Okay? And an important note here, remember I grounded the source. So in this case, let me just make this point clear. VGS is equal to VG because V source is 0. Okay, so VG is equal to VGS and we're setting that to 1.7 volts for the purposes of this example. Okay, so just keep all of that in mind. So our device is turned on. So what happens when the device is on? What does that mean? What does that mean physically? How do we see that the device is on? Well, if we apply some positive voltage, which we've got 1.7 volts applied to the gate, then we're going to accumulate positive charge on this conductive plate up here. Well, our P-type substrate right now has an abundance of holes. So we've got some holes here And those holes are separating this heavily doped N-type region from this other heavily doped N-type region. But we want to connect those right now so that we can pass current between the source and the drain. So in this case, what's going to happen, since we have this positive charge here, electrons have a negative charge. So they are attracted to this positive charge. So even though it's a p-type substrate, we're going to get electrons moving toward this plate. What's going to happen is as those electrons move, they're going to recombine with these holes that are close to our gate up here. So what does that do when they recombine? We don't really see those anymore. Okay, so we don't see the effect of those holes anymore, and we're going to keep on getting more and more electrons in this region. So we just see a bunch of electrons flooding this area. So what happens when we have electrons flooding this area? We basically create a bridge between the two N+ regions, because now we have a bunch of electrons in here. This basically also just looks like an N+ region now. So now we have this big giant N+ region. So we just have this big channel connecting the source and the drain. And so now we can actually have current flow between the source and the drain. So let me erase some stuff here to make some room, because there's a bit more explanation involved here. So we've got this channel, right? That's the first thing. And electrons are going to start flowing from the source to the drain. That's the first thing. So we see electrons flowing from the source to the drain, and hence the naming convention. So the source is the source of electrons, and the drain collects the electrons. It's just like, going back to our water flow analogy from Studio 7, it's just like, your shower head might be the source of the water, and then you have the drain that collects all the water. Same thing. So electrons are flowing from the source to the drain, and by convention, we then say that current is flowing in the opposite direction from the drain to the source. So this is the direction of current flow that I'm drawing in orange here. And that's just a convention, okay? So we just see that current flow is opposite to the direction of electron flow. All right, so that's what happens. So our device is turned on. Great. So now there are a few more interesting dynamics going on here than what we've seen so far. So let me start erasing some more stuff. So now we know what direction electrons are going in and what direction current's going in. So now let's talk about another interesting phenomenon that's going to take place here. So as it turns out, this region where the N and the P regions butt up against each other, this is going to create something that we refer to as a depletion region. So what does that mean? Let's draw this out a little bit. So let's say we have some boundary like this in our device, which we do. So we have an N region and a P region coming together. So we know that that N region has all of these extra electrons, and that P region has a bunch of extra holes. Well, our two materials want to go to the state of high stability at equilibrium. And so what's going to happen is these electrons and holes at this boundary, they're going to want to recombine with each other. And when that happens, we see, an electron over here comes over to this hole and recombines and knocks that one out. And so we just see this region where we've eliminated all the electrons and holes along that boundary. They've all recombined. And so we see this region that I'm highlighting right now at that boundary called the depletion region, because we no longer have an excess of electrons or holes. We've reached this equilibrium state in this region. So this is our depletion region. So the same thing is going to happen in our NMOS device when we've got these wells butting up against our p-type substrate. Now, that's all fine and good, but in order to actually have current flow between the source and the drain, we need to have a potential difference between the source and the drain, right? So let's set V drain to source. So that's the voltage difference between the drain and the source. And in this case, since the source is at ground, VDS is equal to VD. And let's say that's 2 volts, just choosing a random number, okay? So now we have a higher potential area at the drain and a lower potential area at the source. The device is turned on because the gate voltage is above the threshold voltage, and so now we will see current flow from the source to, from the drain to the source, from region of high potential to the region of low potential. But something interesting is going to happen with our depletion region now. So now we have this positive potential applied to the drain. Well, what is that going to do? The electrons in the p-type substrate are going to be attracted to that positive potential right here at this N+ well, just as they are attracted to the positive potential at the gate. So now we'll see more electrons flooding this boundary area. And what is that going to do? That's going to grow our depletion region. So now our depletion region is going to be even larger right here. And unfortunately, this is also going to affect the channel that we created between these two N+ wells. So what happens is we'll see very close to the drain, we'll see a very wide depletion region, and that's going to taper off as we get farther and farther away from the drain. So it'll eventually taper off like this. Okay, and so you can see that our channel actually kind of looks like this. It sort of tapers off as we get closer to the drain. So as it turns out, as we increase the drain voltage, initially, we will get more current flow, which we would expect by Ohm's law, because there's a linear relationship, right? V equals IR. If the voltage difference between the drain and the source grows, then we're going to see more current flowing through those terminals. Unfortunately, as we increase the voltage at the drain, we start to get a wider and wider depletion region, which is going to cause a pinch-off effect right here. And so what you might expect is that this pinch-off would cause basically current to stop flowing at some point because the depletion region has expanded so much. Luckily, that doesn't happen. But what does happen is these electrons continue to bombard this region, and this pinch-off effect is going to cause this channel to be really narrow here. So at some point, this channel is going to reach some point where it's super narrow here, and we just can't get any more current from the source to the drain, no matter how much potential difference we apply between the drain and the source. So I can apply, 10 volts here, and the current will remain the same because of this pinch-off effect. We just can't get any more current to flow between the source and the drain at some point because of that depletion region growing as we increase the potential difference between the drain and the source. So this is an unfortunate reality, and we call this effect saturation. So when we get this pinch-off effect where we've maxed out our current no matter how large we set VDS, we call that saturation. So let's sort of draw this out graphically so we can better understand what's going on here. So essentially what we've got here is we have some current, we'll call it ID, so just the current through the drain. So that current that we just looked at, and I'll even draw it back in here. So the current goes like this. This is ID, opposite the flow of electrons, just like we said before. And this will be VDS. So this is the potential difference between the drain and the source. So it's VD minus VS, right? Just as we've been saying up here, right here. All right. So now, if VGS is less than the threshold, then we're not going to get any current no matter how large we make VDS. So our curve is going to sort of flatline right here. So that flat line is basically for every value VGS is less than V threshold. So if the device is not turned on, then we're not going to get any current flow at all. Now, once we turn on the device, so here we've got VGS set to 1.7, which means that V threshold VGS minus V threshold is like 1 volt, because we said that V threshold was 0.7. So initially what we see here is if we got the device turned on like we do, we see as we increase VDS, the current increases linearly, like we expect as a result of Ohm's law. But at some point, that pinch-off effect kills us, and we can no longer get any more current no matter how much we increase VDS. So it flatlines, and this is saturation. So that flat line area is the saturation region. And we'll say that this line represents VGS minus VTH is 1, which is what we have here. And to be super clear, I'll say VTHN. Okay, so that's VGS minus VTH equals 1. Now, what do we do if we need more current to flow from the source to the drain? Well, we can just increase the value of VGS, right? We can just have a higher potential difference between the gate and the source, because that will increase the width of our channel between our two wells. So if we increase VGS minus VTH, then we'll see another curve which moves up. So now we can get more current across those two terminals. So maybe this is VGS minus VTH equals 2, and so on. You kind of get the idea here. So if I continue increasing this, I'll just continue to grow these curves. So this might be, VGS minus VTH equals 3, and so on and so forth. Now, these points where we reach this saturation area, we can kind of connect those and draw in a line here. So everything to the right of that orange line I just drew is referred to as the saturation region. So this is saturation. And everything to the left of that orange line is referred to as the triode region. So this is the triode region. Okay, so that's just some terminology to keep in mind here. So let's kind of sum up the results that we've gathered so far. So far we said that for an NMOS device, in order for it to be on, let me just move this down here. So in order for it to be on, we need to have VGS is greater than V threshold N. If the device is to be off, then we'll have that VGS is less than V threshold N. So if we're in the saturation region, it turns out that we're in the saturation region if VDS is greater than VGS minus VTH. And we're in the triode region if VDS is less than VGS minus VTH. And note once again that here VTHN is positive. It'll be some positive voltage. Okay? So this gives you, I think, a pretty thorough understanding of the function of an NMOS device. So now let's quickly go over PMOS devices, which are basically just going to be the dual to this. So for a PMOS device, everything is basically flipped. So instead of having N plus regions, we have P plus regions. So we'll have these wells once again, and they'll be P plus, and we'll have some substrate down here, and this will be lightly doped N-type. Once again, we'll have our insulative layer here. We'll have our gate, conductive material up here with our gate. And we'll have a drain and a source. Okay? Now, if the device is to be on, then in this case, VGS needs to be less than VTH, and I'll say VTHP. Note here that VTHP is negative, okay? So VGS needs to be less than whatever VTHP is. So it's opposite of what we just said for the NMOS device, just like we went over in Studio 8, right? Because PMOS devices turn on when a logical low is applied to the gate. So we expect that to be negative, VGS to be negative, okay? So now, in this case, we have an abundance of electrons here, and we have abundance of holes in these P plus regions. So now in this case, when we apply a negative voltage to the gate, we get a buildup of negative charge, and holes are attracted to this region. So now we create a channel of holes instead of electrons. And in this case, we see the holes moving like this. And once again, the body is always hooked up to the source. So keep that in mind as well. So we see our holes moving like this, and our current is actually going to move in the same direction in this case. Because you can also think of this as the electrons are moving in the opposite direction of the holes, right? So our current ID is like this. So that's how our PMOS device is going to work. And also note here that VD is going to be less than VS in order to get current flow. Okay, so for this device to be on, we have that VGS is less than VTHP, and it's off if VGS is greater than VTHP. And for saturation and triode, we're just going to flip the inequalities just like we just did for our on and off conditions. So here we'll just flip these inequalities around just like this. So this tells us whether we're in saturation or triode. So that is NMOS, or I'm sorry, that's PMOS. So now hopefully this gives you a pretty thorough understanding of how these devices are working physically. Okay, so before we move on, I made one more promise in Studio 8, which is that I would explain why it is exactly that PMOS devices are better at passing a logical 1 from the drain to the source, and NMOS devices are better at passing a logical 0 between the drain and the source. So what I thought I would do here to try to explain some of this is to take a look at our most simple pull-up, pull-down network structure, which is the inverter. So normally what we have with the inverter, right, is we have our input here, and then essentially we are going to have a PMOS device here. And as a reminder, this is the source, this is the drain, this is going to be VDD. And then here is where our output will be. And then we've got our NMOS device on the bottom, and that's the drain, and that's the source, and this goes to ground. So this is our inverter structure that we already know and have discussed. Okay, but what would happen if we flip the location of these two devices? So put the NMOS on top and the PMOS on the bottom. So if we do that, we're not going to have an inverter anymore. That's the first thing. So in this case, what we would have is a buffer. Okay, so it's just simply we expect the input to equal we expect the output to equal whatever the input is, okay? So let's flip these around. Okay, so in this case, we'll have in coming through here, and we'll have our NMOS up top, and there's VDD. There we are, there's our output, and we'll put our PMOS at the bottom. Okay, so there we go. So there's a proposed design for the buffer. Let's see what happens. So if I put VDD at the input, let me change colors here. So I put VDD at the input, then I expect to get VDD at the output, okay? Because we want a strong logical high signal to pass, because this is a buffer. So we expect VDD at the output. But there's an interesting thing that happens. Let me label everything here. So this is the drain, this is the source, drain, and here's the NMOS, here's the PMOS. And there's something interesting that happens. So when this device is turned on, so the top device is in fact turned on and the bottom device is turned off. So we'll ignore the bottom device for now. So let's just focus on that top NMOS device. So that device is definitely turned on because the input is at VDD. And what's going to happen is as this device turns on, the drain and the source are going to be connected. And so the source is going to move toward VDD. And on its way there, it's going to pass a critical point. So we pass critical point when VS is equal to VDD minus VTH. So when this happens, let's take a look at what VGS is. So VGS, so we know what the gate is. The gate is at VDD. So gate minus source. So we just wrote out what the source was here. So we're going to do VDD minus VTH. And sure enough, we see that the gate is at the threshold. So what this tells us is that if we go any higher on the source, our NMOS transistor will turn off. So what this tells us is we can go no higher on the output. We can get no higher than VDD minus V threshold. That's the highest we can go. If we go any higher than that, everything will turn off. So just to put some real numbers into this, let's say that VDD is 5 volts in this case, and we'll leave V threshold at 0.7 like we said before. So if that's the case, then we've got 5 minus 0.7, that's gonna be 4.3. So according to this, the highest we can get on the output with VDD as the input is 4.3. That's the highest we can go. We can't go any higher than that because the NMOS transistor will turn off otherwise. Now the PMOS transistor reaches a critical point. So now let's flip this around. Okay, so we're gonna expect something else. So let's put 0 volts on the input. So now this NMOS device is definitely turned off. We expect to see 0 volts on the output because it is a buffer, as I said before. However, let's see what actually happens. So on its way down to 0 volts, the source, because these are connected now, right? We have a connection between the drain and the source on that PMOS device. So the source is going to go towards 0 volts from whatever it was at before. So it's going to move towards 0 volts, and on its way there, it's going to pass the threshold. So at these thresholds, so we have a new critical point. Critical point at Vs is equal to Vth, and we'll leave that as 0.7. Okay, so it's positive 0.7. So now at that point, VGS, so we know the gate is at 0, and Vs is at V threshold. So guess what? VGS is negative V threshold. So it's just barely on. So this is right at that critical point between on and off for the PMOS device. Because remember, for the PMOS device, we need a negative value for V threshold. So we need negative 0.7. So this is the point, this is as low as we can go on the output. We will never get to 0 on the output. We can only go as low as 0.7. So our expected values, I'll leave in blue here. So we expected to be able to go on the output from 0 volts to 5 volts. In reality, we can only go 4.3 volts down to 0.7 volts. So this is the reason that we structure our CMOS pull down networks the way that we do with the PMOS device up top and the NMOS device at the bottom, because this allows us to get full rail-to-rail output swings. So we can get full 5 volts out and 0 volts out instead of these unideal values like 4.3 volts and 0.7 volts. Okay, so before we jump back into digital logic and digital circuits, which is where we left off in Studio 8, I want to briefly just mention that today we talked about MOSFETs, and we talked about NMOS and PMOS devices specifically. But there are other types of transistors. So we chose to talk about MOSFETs exclusively because of time constraints really, but also MOSFETs are used so widely in digital electronics that this is probably, given the time, the most appropriate one to choose if we have to choose one. But there are other very useful types of transistors, including bipolar transistors and also JFETs. And you can see both of those depicted on the slide here, their physical structure. I don't want to get into describing any of these things, but just so you know, there are other types of transistors out there which are used for different applications as well. Okay, so a quick note on future course suggestions. So as always, we barely scratched the surface on any of this. There's a lot more going on with the physical structure of MOSFETs. We didn't talk about diffusion, we didn't talk about drift currents, we didn't talk about electric fields, we didn't talk about so many different things. And so there's a lot more to talk about there, and for more on that, you can see courses like, or students can see courses like Engine 1620. The first week of that is semiconductor device stuff, and then really most of the course is focused on building circuits with transistors, so talking about amplifiers, filters, etc. Okay, and then Engine 1590 is exclusively about semiconductor devices. So if students want more about that material side and more about the semiconductor side, that is a good course to go to as well. Okay, all All right, so now let's jump back into our digital logic discussion, which is where we left off in the last studio. Okay, so last time, quick recap. We talked about three main gates last time. That was our primary focus. And those gates were the NOT gate, or the inverter, which you see here, the AND gate, which you see here, and the OR gate, which you see here. So I'm not going to go through these gates again, but if you need a refresher, feel free to go back to the Studio 8 video because those are discussed pretty extensively in that video. Okay, so to save time, I'm going to move on from that. Okay, gates and bubbles. So this is another thing that we actually talked about last time. I decided to throw it in there at the end of the video. But just a quick recap on this. So anytime you see a bubble, which is this little circle, right, on a gate, it just means not. So we can build more gates, NAND gates, which just means not AND. So it's the opposite of an AND gate. And we can build not OR gates, which is the opposite of an OR gate. And as we saw, these are actually less expensive to build in hardware than their AND and OR counterparts. So that's just an interesting note. Also, just a quick reminder that the bubble always means not. Same deal goes for the PMOS, that symbol in digital circuits for the PMOS with that bubble. Basically what we're saying there is like a not NMOS, if you want to think about it like that. Okay, so anytime you see a bubble, that means not. Okay, so another gate that's going to be useful, because in a few minutes here we're going to be talking about some useful circuits that we can actually start building out of our gates. So we've talked a lot about different types of gates, and this is the last one that we're going to talk about. There are more, and the others are pretty self-explanatory once you get the basics of these gates. So this last gate, before we get into things like adder circuits and multiplexers, and then building more complex circuits with those components, we need to talk about the XOR gate. So the XOR gate is exclusive OR, and you can see the symbol for it here. So this is how we write it out in Boolean algebra. So we have, the output Y is equal to A, and then it's plus, just like the OR gate, except it has this circle around it. So that tells you it's the exclusive OR gate. And then B. Okay, so that's how you write it, and it's an exclusive OR gate. Okay, so what that means is basically the input can one of the inputs can be 1, and one of the inputs must be 0. So one of the inputs must be 1, and one of the inputs must be 0 in order for the output to be 1. So A or B can be 1, but not both. That basically sums it up more concisely, and you can see that in the truth table here. So it's basically the same as an OR gate, except for this last row. So with the normal OR gate, this would also be 1, but with the exclusive OR gate, if A and B are both 1, then the output is 0. So that's the exclusive OR gate, and yeah, that's how it works. So we won't go over the transistor structure for this one, but that is another exercise that you could do. Okay? All right, so now before we talk about adders, we need to go over the binary number system a little bit. So I feel like I've said this like 1,000 times, but there is more going on even with the binary number system than what we are actually going to talk about right now. So what we're going to talk about is the most basic rules for binary numbers. We're just going to talk about positive binary numbers. Unsigned is the more precise term for this. So no negative numbers, just positive, just the bare basics on how to use the binary number system, just so we can talk about adders and adder circuits. Okay? So basically, the first thing I want to say is we're all used to using a base 10 system, right? So let's take a number like 22 in base 10. So a lot of times I'll write a subscript 10 right here so that you know that I'm talking about base 10. And if I was talking about binary, I'd write a little 2 there in the subscript. Okay, to keep this a little less confusing though, I'm just going to get rid of that. So know that this is in base 10. So in base 10, we have the number 22. Well, what does that look like? Well, this place is really the 10 to the 0th place. And this place is the 10 to the 1st place. So if we break this thing down, what we really have is 2 times 10 to the 1st plus 2 times 10 to the 0. And so in this case, we get 2 times 10 to the 1st is 20, plus 2 times 10 to the 0 is 2 times 1, which is 2. And so there we go. We have 22. So that is kind of how you can decompose the number 22 based on the fact that we're using a base 10 system. So now if we're using a binary system, so in our system, the one that we're used to with base 10, each of these digits can take values between 0 and 9, so there are 10 possibilities. In a base 2 system, in a binary system, there are only 2 possibilities for each of these places. And you can see how the places work. So the first place here is the 2 to the 0th place. Then it's the 2 to the first place and the 2 to the second place, and so on and so forth. You just kind of move up in the same way that a base 10 system would work. But instead of having 0 through 9, I only have 0 and 1. Those are the only 2 possibilities I have. So basically, the whole idea with binary is we want to go from a base 10 system, which is what we're used to operating in, to a system with just 1s and 0s so that we can do calculations with gates and build computing systems. So let's get rid of this base 10 stuff and look at the example on the slide. So also a quick note, I kind of circled just randomly one of these and said this is a bit. So if you don't know, if you've never heard this term explicitly before, a bit is just referring to a 1 or a 0. Okay, that's what I mean when I say bit. If I said 4-bit number, then I'd grab 4 bits. That's what I mean. Okay. So in this case, we have a 7-bit number, and I would say it's a mystery, but the answer is actually on the slide. But anyway, we'll still go through it. So let's start with this place here. So we see we have a 1 here. So that's going to be 1 times 2 to the 6th plus 0 times 2 to the 5th. I'm not going to write that out because it's just 0. Plus 1 times 2 to the 4th plus 1 times 2 to the 3rd, and then plus 0 plus 1 times 2 to the 0. Okay, and what that's going to equate to, 2 to the 6th is 64, plus 2 to the 4th is 16, plus 2 to the 3rd is 8, plus 2 to the 0 is 1, and if you add all that up, we're going to get to 89. So that number right here is 89 in base 10. Okay, and you can see the little subscript 2 right here. If we wanted to, you could write a subscript 10 right there. But anyway, that's what that means. So this is how we use binary. Now, one other thing I want to say has to do with how we add binary numbers. So I just want to point out that this really works the same way as base 10, but it can be like slightly confusing when you first see it. So I just want to go over it really quickly. So let's say in base 10, I'm adding something like, 19 and 2. So if I have that, then I have, I go 9 plus 2 is 11. So I put 1 and then I carry the 1. And then 1 plus 1 is 2. So I get 21. Well, in binary, it works the same way. So just remember that you still have to do carries just like we do with a base 10 system. So let's say I'm adding 1 and 0. If I add 1 and 0, then the answer is just 1. There is no carry. Okay? And so in binary, 1 is just 1. And 0 is 0, so the answer should be 1, and that's the same as in base 10. So now what if I'm adding 1 plus 1? So we expect the answer to be 2. Let's see if we can do this in binary though. So 1 plus 1 is actually going to be 0, carry the 1. So we end up with this, 1, 0. And let's see if that is 2 in decimal. So this place is the 2 to the first place. And this place is the 2 to the 0th place. So we have 1 times 2 to the first is 2. So in fact, it is 2. Okay, I want to give one more example. So what if we have 3 1s? So if we add these two, we get 0, carry the 1. And then we add 0 plus 1 is 1. So we have 1, 1. Okay, so 1 plus 1 plus 1 is 3. And is this 3 in binary? Well, yes, it is, because that's 2 to the first plus 2 to the 0, which is in fact 3. So that checks out as well. Just a quick note on how you add things and how you use the binary number system for unsigned binary numbers. Okay, now that we've gone over that, let's go over some adder circuits. So we're gonna start simple here and then we'll work our way up to the full adder. So this is the half adder. So the half adder basically just adds these 2 bits and it tells me what the sum is and what my carry is. So you see that carry like we did just a second ago? This is exactly that. It's just performing that function for us. So let's see if this makes sense. So this is our truth table, and you can see it makes sense. It's following the same rules of what we just did. It's just written out in a tabular format. So 0 plus 0 is 0, carry 0. 0 plus 1 is going to be 1, carry 0. Same deal for 1 plus 0. 1 plus 1 is going to be 0, carry 1. That all makes sense. The same thing we just went over. Okay, so now let's take a look at how this works with the gates. So let's verify that these gates actually do perform this function when set up in this way. So first thing I'm going to do is I'm going to say, what happens when A is 0 and B is 0. Okay, so I'm going to use blue for zeros, lines that are at 0, and I'm going to use red for lines that are at 1. Okay, so now 0 exclusive ORed with 0 is what? It's 0. So the sum is 0. These are going to propagate down. 0 and 0 is 0. And that matches our table. So we're good there. Okay, let's go to the next combination. 0 and 1. So this is going to propagate through like this. My 1 is going to propagate through like this. 0 and 1 is actually 1. All right, and I mean to say and 0 exclusive ORed with 1 is 1. Then this is going to propagate down like this. My 0 is here. 0 and 1 is 0. So I have a 1 carry of 0. That matches my table. So we're good with that combination. Okay. So now let's do 1 and 0. So this node is at 1. And then we expect to get the same thing as we just got, actually. So that node's at 0. Here we go. There we are. So 0 exclusive ORed with 1 is going to be 1, and 1 ANDed with 0 is just 0, so we get the same thing. That adds up, matching our table. Okay, so last combination, what if we have 1 and 1? So both inputs are 1. So here we go. So 1 exclusive ORed with 1 is 0, because remember, this is not an OR gate, it's an exclusive OR gate. So if they're both 1, then the output is 0. 1 and 1 is 1. Okay? So we get 0, carry the 1. Makes sense. So you can see that this is adding my 2 bits, just as I specified, but there's a problem. What if I want to add a 3-bit binary number to a 3-bit binary number? Well, in that case, I need to cascade my adders together so that I can get to these higher bit numbers. But this adder doesn't have a carry in. So normally what I do is I route my carry out from the first bit over to my second adder circuit. So this will be my other adder circuit, and this will become my carry in. But there's no carry in on the half adder. So we're really just limited to adding these 2 bits. And we can never do anything with carry ins, okay? So the full adder is going to solve this problem. So now we can add 3 bits together, and the main purpose of this is just so we can do what I just said, which is to string a bunch of adders together and add larger numbers. And when we do that, we create something called a ripple carry adder, okay? So let's see how this works. So basically the point is, if I have 1, 1, and then from my previous operation, maybe I have a carry of 1, I expect my sum to be 1 and my carry out to be 1. Okay, so because I'm adding 1, 1, and 1. So these 3 numbers are being added, these 3 bits are being added, and we get the output here. Okay, that's basically what's happening. So let's just do like 2 combinations. We'll go through. I'm not going to do all of them because it would take us way too long, but you'll get the idea. Hopefully you're already getting the idea from doing the half adder of how this is working. So let's just choose 2 to do. So I'm going to choose the second row here to do first. So what if A is 0, B is 0, and Cn is 1? What's going to happen? So 0 exclusive ORed with 0 is 0. Then 0 is going to propagate down here. 0 ANDed with 0 is 0. So that node is at 0 still. This is coming down here. Cn is at 1. So that brings this node to 1. 0 exclusive ORed with 1 is actually 1. Okay. And 0 ANDed with 1 is 0. And 0 or 0 is 0. So I get 1, 0, bam, that matches my truth table, as we expect. Okay, so let me erase all that and go to another combination. So let's try this last combination and see if that one holds up, that last row. So what happens when everything's 1? So A is 1, B is 1, and Cn is 1. Okay, so in that case, I'm just going to draw in my red lines to make this as clear as possible. All right, so 1 exclusive OR with 1 is 0, because remember, again, this is not an OR gate, it's an exclusive OR. So that's going to give us a 0 line here. And that's going to be at 1. 1 ANDed with 1 is 1, so this is 1. All right, 0 and 1 is 0, so this line's at 0. 1 and 0 is 0, so this is at 0. Or I'm sorry, this is at 1, I meant to say. Okay. 1 exclusive OR with 0 is 1. So in fact, we do get exactly what we thought we would get based on the truth table. Okay, and you can go through all of the combinations in the truth table and just trace out what's going on, how the wires, how the signals are propagating through the gates, just like I just showed. Okay. All right, so there's the full adder, so we can add 3 bits now. Okay, so another very useful function, very useful basic foundational block that we can build is called a multiplexer. And a multiplexer is kind of like an if in code. So if you're used to coding, it's basically that. Anytime you see that if, that's kind of the functionality that a multiplexer has. So what a multiplexer does is it has 2 inputs. So this is a very simple multiplexer. It's just a 1-bit input multiplexer. We can have many more bits, and that'll change the number of bits in my select line as well. This is just the simplest case. So what it does is it uses this select line here to choose between whether the output is going to be equal to whatever 0 or in 0 is, or whether it'll be in 1. So if the select bit is 0, then in 0 will propagate to the output. If, on the other hand, the select bit is equal to 1, then in 1 will propagate to the output instead. So a multiplexer just lets us choose which of a group of signals is being routed to the output. Okay? So that is what it does. Now this is how you build it using gates. So I didn't include a truth table for this one, but I do want to explain intuitively how this is functioning still. So let's take a look here. So we've got the select line and we've got our 2 inputs. Okay. So you notice our select line is inverted. So right off the bat, our select line is inverted right here. And then we've got 2 AND gates and an OR gate. So what is this going to do? Well, let's say our select line is 0. Okay, so if our select line is 0, so this is going to go to 0, all of this, and this node is going to go to 1. So whatever in 0 is going to pass through this AND gate, and then since this is an OR gate, it's going to pass through there to go to the output. Now, because once again, this node is at 1, and with an AND gate, 1 and whatever the other number is going to be, the output will be whatever that other number is. So if I have 1 ANDed with A, or here, I'll write this in a more proper way, Boolean algebra format here. So if I have 1 and A in Boolean algebra, that is just A. Okay, it's just always going to be whatever the number is, other number is. So this is what I mean by other number here. So we notice that this is at 1. So therefore, whatever in 0 is going to pass through my AND gate. It's going to propagate through here, and it's going to propagate through my OR gate and go to the output. Okay, and the reason that's going to happen is that this node coming out of this AND gate is definitely going to be at 0. And why is that? Because, well, my select line put a 0 right into this AND gate. So the output of that AND gate will definitely be 0. So that's how that's working. Now let's say that instead of this, my select line is at 1. So if that's the case, then this is 1, this is 1. It's going to invert, so that's 0. So in this case, it's choosing whatever input number 1 is, because I've put the 1 signal at this AND gate, and I put a 0 signal at this AND gate. So this AND gate is definitely going to pass a 0 here. And this AND gate is going to pass whatever in1 is through to here, and that's going to go to my output. So that's kind of a quick intuitive explanation of how this multiplexer is functioning. If you wanted to draw out a truth table and go through all the possibilities, then you could, but this is a multiplexer. And the most important thing is really just to understand what functionality it has, which is just to choose between 2 inputs or more. Okay. All right. So now things are going to get a little bit more interesting. So far we've talked about combinational logic. So now combinational logic is just gates. So when we just have gates, then we have combinational logic. Signals are propagating through the gates. There's no concept of memory or anything like that. Now we can add flip-flops into the mix. So this is a DFF, D flip-flop. And what that's going to do is allow us to create sequential logic. So now we can add clocks into the mix, and we have some concept of memory. So with the D flip-flop, it has the ability to store a value until the next rising edge of the clock. So the way this works, you can see my clock is coming in here, and my clock signal will be a square wave. It looks like this, okay? So on the rising edge of the clock, which are these edges here, so let me just highlight those. So on these rising edges, this is the only time that the D flip-flop turns on. Okay, and what I mean by that is this, when it sees the rising edge of this clock, D here, this input signal, passes through to Q. Now, once that rising edge is gone, that data is stored in Q until the next rising edge of the clock. At that point, once again, D will pass through and Q will assume a new value. So we can actually store data as long as the power is turned on, of course, to the D flip-flop. You don't even see the power lines in here, but actually this chip will be connected to VDD and ground. So as long as that's connected, it'll store memory until the next rising edge of a clock comes. Now, it doesn't have to be a clock. We could hook up the clock to a push button, and that can provide my rising edge. So when I push my push button, that provides that signal jump from 0 to 1, and that operates my flip-flop. So lots of different ways to set this up, but just to kind of do a quick simulation here. So let's say that I have D is, so first of all, let's say Q is at 0. Okay, and D is at 1. So right now we are at this point on the clock, let's say. So now, as time moves on, we're gonna move, the clock's going, and boom, we hit the rising edge of the clock. When the rising edge comes, Q is going to become 1, and D is going to become whatever the new value of D is. I don't know what that is. Could be a wide variety of things. It's up to the rest of the circuit to give the D flip-flop a new value for D. So let's say that new value is 0, okay? Let's say it's 0 now. So now we're here. Let me erase this so it's a little less confusing. So we're here, we're at the rising edge of the clock, and it's gone. Okay, so the rising edge has passed. Okay, so Q is holding its value. D could be changing this entire time. We have no idea what D is. It could be, D could be 1 right now, and Q is going to hold its value. I'm going to come back around. Okay, so we're here, and let's say like right now, so D just changed to 1 in the middle of my clock changing. Now we're going to change it back to 0. Doesn't matter. Q doesn't see any of this. Boom, we hit the rising edge of the clock. Well, now, whatever D is, that's going to become the value of Q. So let's erase this, and Q is going to be 0 now. Okay, so you see how this works? Basically, whatever the value of D is when the rising edge of the clock comes, that will be captured in Q until the next rising edge of the clock. D can change all at once when we're not at the rising edge of the clock and nothing will happen. Q will maintain its value, but as soon as the rising edge comes, that value will be captured in Q and saved until the next rising edge comes. So now we have this idea of memory and we can create these type of sequential logic circuits. Okay, so now that we've covered a variety of foundational sort of building blocks that will enable us to build some different digital circuits and digital logic, let's actually go through a few example problems and see how we can use these foundational blocks to build real circuits. So our first example, as you can see on the slide here, is we want to build a circuit that basically counts by ones starting from 0 whenever we push a push button. So whenever we push a push button, we want the counter to increment. So it's essentially counting the number of times that we push the push button, if you want to think about it that way. So the way to do this, so let's come into Logisim now. So this is Logisim. So the UI, it's pretty simple, I think. I think it'll be a pretty easy tool to use for this studio, at least I hope. And so let's sort of start building out some of these foundational building blocks that we've been talking about. So to create this circuit, we're going to first need to create a full adder. To create a full adder, we first are going to need to get to a half adder. So let's start with that. So let's build our half adder in Logisim. So in Logisim, you can see we've got a variety of folders over here, and we're going to come into gates, and we're going to grab an XOR gate. And I like to change the size of the gates. You can make them smaller. It does not matter. It doesn't change anything. And I'm not going to mess with any of these other options for now. And then I'm going to grab an AND gate. I'm going to bring that over and make that smaller as well. Just my personal preference. You don't have to do that. And then I'm going to connect everything together. So you can see I'm just dragging from these nodes to create wires. There's also a wire tool which you can use if you want, which allows you to just click on the nodes and make wires that way. I'm going to drag them. I think it's a little easier, but it doesn't really matter. Whichever way you want to do it is fine. And so here we go. So now I have created my half adder. So what I'm going to do now is I'm going to add some probes. I'm going to come into wiring and hit pin, sorry, not probe. So pin, and then I'm going to put 2 of these here. And you can see now everything is dark green, which tells me that I'm at a logic level 0 on all of those nodes. But now what I can do, so you can see I came up here and I clicked on this pointer finger button. And this tells Logisim that I'm in simulation mode now. So now I can click on these pins and my circuit will start doing things and lighting up. So you can see I clicked this, so that's a logic level 1 now, and that bright green means logic level 1. So what am I doing? I'm adding 1 and 0, because remember this is like my first input, this is my second input, this is my sum, and this is my carry for the half adder. So this is 1 plus 0, which is a sum of 1, carry of 0. Same thing for 0 plus 1. And then I can do 1 plus 1, which is a sum of 0 and a carry of 1. So this is pretty cool. It's very visual. You can kind of see how signals are actually propagating between the gates in your circuit. And so I'm hoping this will be a good teaching tool for the purposes of this studio. So let me go ahead and delete these pins for now. And let's continue on. So we built the half adder. Now let's build our full adder. So what I'm going to do, I'm just going to copy this XOR gate. So Command C, Command V. I'm going to bring that over. So copying things will make your life a lot easier and make things go a lot faster as you're building circuits out in Logisim. So I highly recommend that you do that, especially during studio when we're really pressed on time. So I'm just going to simply create the circuit for my full adder. That's all I'm doing right now. Here we go. And this guy is going to come over here. And I'm going to need an OR gate. So I'm going to come out of wiring, go into gates, OR gate, change the size, and put that in there. Okay, so there's my sum, there's my carry out. Now I have a carry in. Okay, so let's put some pins on this thing and make sure it works as we expect. So there's a pin. I'm just going to copy that thing and move it here. And we'll grab one more, put it here. Okay, so I'm going to come into simulation mode by clicking on my little pointer finger icon. And I can sort of simulate how this works. So we can add 1 plus 1, same deal as with the half adder. It gives us a sum of 0 and a carry of 1. 1 plus 1 plus 1, so if Cn is 1, then we get a sum of 1 and a carry out of 1. So you can see we can kind of go through and actually simulate what's going on for each of our inputs. And if you go through the full truth table for the full adder, you'll see that it does match up, and we'll see those signals actually propagating live in Logic. So that's pretty cool. So now we can actually see things visually. So once again, I'm going to delete these pins. So there we go. So now we've got our half adder. So now we can kind of move forward with actually solving this problem. So the first thing we need to decide is how many bits we want our output to be. And this is going to basically determine the max output value, the max number that we can count to. So I'm going to choose to sort of keep this simple and say that the max number, that the number of bits we'll have is 3. So now if we have a 3-bit number, what is the max number? Well, it's 7, because the max would be 111, and 111 in binary, from binary to decimal is 7. Okay, so 111 in binary is 7 in decimal. So the max we'll be able to count to is 7. So we'll go from 0 to 7 every time we push the push button. It'll increment and it'll reset as soon as we go above 7. So what I'm going to do is I'm going to highlight my half adder. I'm going to need 3 of them, because remember, this only adds these 2 bits plus the Cn. I need 3 bits. So I'm going to need 3 full adders. So what I'm going to do, I'm going to highlight this entire thing, Command C, Command V, and I'm just going to drag this thing down. And then I'm going to grab another one, Command V, pull that thing down. There we go. So now I've got 3 full adders on the screen here. And now I just need to start connecting these things together. So first of all, let me just kind of explain what's going on here a little bit more. So here up top, this first full adder is the 2 to the 0 place. So this is input number 1 and this is input number 2. This is the 2 to the 0 place for the first input. This is the 2 to the 0 place for the second input. And the second full adder is going to be same deal, but 2 to the first place. So this is 2 to the first place for the first input, 2 to the first place for the second input, carry in for this full adder. Then we have the 2 to the second place right here. So this will be 2 to the second place for the first input, 2 to the second place for the second input right here. So that's how this is going to work. Now the other thing we're going to do, the reason that this carry in was so important, and why it was a problem that we didn't have it with our half adder, is that we need our carry out from the lower bit value to propagate over to the carry in on our next place up. So the 2 to the 0, carry out from the 2 to the 0 place is going to need to propagate over to my carry in for my 2 to the first place. And the carry out for my 2 to the first place full adder is going to propagate over to my carry in for my 2 to the second place full adder. And that makes sense. This is exactly the same thing that we do when we paper and pencil add in binary, like I was going over before. So, carries, they transfer over to the next place, and that's exactly what we're doing physically in the circuit here, okay? So now, the carry in on the first full adder, you might be wondering what's going to happen with that. Well, there is no carry in for that one, so what we're going to do is we're just going to put a ground there. So that'll be a logic 0. The carry in is just always 0 for that one because there's nothing that comes before. Okay, so now what we're going to do is we need some way to establish a constant 1, because every time we're incrementing our counter by 1. We could increment it by some other value. We're keeping it simple here, and we're just going to increment it by 1. So how do we create a 1? Well, I'm going to choose to put my 1 on input B. Remember, input B is like this one in each of these full adders. And so what is a 1? A 3. So in 3 bits, 3-bit binary, how do I represent the number 1? It's 0, 0, 1. So this is going to be 0, this is going to be 0, and this is going to be 1. And that's just a constant. We're always adding 1 to whatever the first input is. So let's do that. So we're going to need a few more grounds. So this is going to be 0. So there's the first 0, 0, and we're going to need a 1 right here. So the 1, you can see I just grab a power. So this little power node just tells me I'm at VDD, so that's a logic level 1. Okay, so now we have all of this set up, and then we've got this node, which is our other input, which is not a constant. So now we need to bring in some sequential components, namely the DFFs. So let's do that. So let's get out of wiring and come down to memory. So in memory, we're gonna find the DFFs. So let's grab 3 of these guys. That's how many we're gonna need because we have 3 bits that we're trying to save during each clock cycle. So we're gonna need 3 DFFs. So let's put these guys out here, and we're just gonna connect the sum pins from each of our full adders to the D pin on each of our DFFs. And now what's gonna happen is the output from the DFFs, each of those is gonna route over to its corresponding input pin on each full adder. So this is creating feedback. And so this is what's gonna allow us to save our state and continue counting. So this is very important, this concept of feedback here. This is how we use DFFs to create more complex circuits and sequential logic. So now that we have this feedback, we can actually increment the value. So the value is constantly being updated as D propagates to Q on each clock cycle. Okay, so now I'm going to connect all the clocks together. So this little triangular bit is the symbol for the clock. So we'll grab all those and connect them together. I'm gonna move this guy out of the way. This, by the way, is the carry out from my last full adder, which isn't actually doing anything. This is useless to me. I'm just gonna leave it. What I could do is delete some of these gates right here, but I'm just gonna leave them. They're just not doing anything. In real hardware, of course, we delete them and get rid of them because we don't wanna be wasting money on extra hardware that we don't need. But in LogSim, it doesn't really matter. So I'm gonna leave them in there. You can delete them if you want. And what I'm gonna do here is now I'm gonna come over to input output and I'm gonna grab a button. So that button is gonna act like my clock. So it's gonna provide a rising edge that will allow D to propagate over to Q. So there we go, there's our button, there's our clock. And I'm also gonna connect up these reset pins. So this we don't have to do, but since we have the reset functionality already built into all of our DFFs, we might as well connect it up and see how it works. So here we go, I've connected up my reset pins, and I'm gonna grab another button, and I'm gonna flip it around here. You can see I'm choosing facing west so that I can connect it up correctly. And there we go. Everything turns dark green, which means everything's connected and good to go. Except for, of course, this part, which is already at a logic level high. Okay, so now when I push this button, we should see everything increment by 1. Now, it's gonna be really hard to see our output right now, so what we're gonna do is we're gonna create a little probe. And this is just a little tool that LogSim has, so I'm gonna grab each bit and I'm gonna bring them closer together, just for practicality reasons. So I'm gonna grab this, just like so. And what I'm gonna do is I'm going to kind of take all these wires and put them into a bus. And a bus is just a collection of wires. So I'm gonna come over to wiring and hit splitter. This is the tool I'm gonna use to do this. So right now we have 2 bits. We need 3 bits, so let's change that. So fan out, we're gonna change to 3. And bit width in, we're gonna change to 3 as well. And then I'm gonna choose facing west. I think that's gonna make my job easier. And I'm just gonna put this guy right in here. There it goes. Okay, so now I can grab this guy. You can see this big fat wire is my bus wire. So this is these 3 bits bundled together into 1 wire now. Well, not 1 wire, but you get the idea. There's just 3 bundled together, okay? So that's why it's got this bigger wire. These bigger wires are bus wires. Okay, so now I'm gonna grab a probe, which is pretty useful. And I'm gonna change the direction on this to west. And this probe is in binary. So that's good, that's all fine and good. But I kind of wanna be a little lazy about this maybe, and I don't wanna have to think about everything in binary. So luckily I don't have to. LogSim allows you to change the radix on the probe. So I'm gonna change this to unsigned decimal so that I can just read it in base 10, which will be easier for me to readily interpret. Okay, so now if I push this button so we can see we're at 0, makes sense. And if I push that button, boom, we increment by 1. If I push it again, now we're at 2, and we keep on going. and you can see all the different signals propagating and changing. So you can sort of look through this, and students can look through this and get a real thorough understanding of how the signals propagate and how each of these components are working. And here we go, we can keep on going. And now we're at 7. And if I go any further, then the actual value here, if it could record 4 bits, would be 1, 0, 0, 0, which is 8. It can't, so it records the last 3 bits, which are all zeros. So this effectively resets my circuit. So once I get to 70, the circuit effectively resets. Now again, I have that reset button, so if I have it in some random state, I have it in 3 here. If I hit reset, it wipes the whole thing back to 0 as well. So pretty cool. Now we've built a little counting circuit. So that is the first problem. Okay, so now the second problem kind of just builds on this problem. So we don't have to like recreate a whole nother circuit. We're just going to continue building on this problem. So as you can see on the slide here, what we want to do is the following. So it says, now suppose that I'd like to turn on an LED only if the output is equal to the number 6. So now how can I modify this circuit to include this functionality? So let's go back to Logisim now. So back in Logisim, we want to detect if the output is equal to 6, and if it is, we'll turn on an LED. So let's create some room here. I'm just going to drag these components out. So here we go. Things got a little messed up, so let me clean this up again. Reconnect everything. Okay, there we go. So we want to check if these lines are at 6. So how do we do that? Well, what is 6 in binary? That's kind of the first question that we need to ask. So 6 in binary is 110. Okay, so that's what it means. That's what it will be. So if this line is at 1, and this line is at 1, and this line is at 0, then we know that we have gotten to 6. And notice how I described that. I said this line is at 1, and this line is at 1, and this line is at 0. I'm saying and for a reason. We're going to use AND gates to check what the value of the output is. This is a very common way to check the value of some series of bits. Okay, we very commonly use AND gates and NOT gates to do this kind of stuff, and OR gates, but today we're just going to use AND gates because we're keeping this pretty simple. But if it was like I wanted to check that it was 6 or 7, then I would have some AND gates to check 6 and 7 separately, and then I'd have an OR gate. Today, once again, we're just going to keep it simple and just stick with AND gates because we only have one thing to check. So let's grab an AND gate. So come into gates, and I'm going to make this guy actually facing north, and I'll make it small, just personal preference once again. Okay, so now I have a few options here. So what we've talked about is 2 input AND gates the whole time. That's all we've talked about so far. But you can actually change the number of inputs in Logisim. So you can create a 3 input AND gate. As you see here, now I have 3 inputs. And that's probably the easiest way to do this. I'm gonna stick with 2 input AND gates because that's all we really talked about in the studio. But just know you can totally just change the number of inputs and do that instead of what I'm about to do. So instead of doing a 3 input AND gate, I'm just gonna cascade 2 AND gates together so that I get to a 3 input AND gate. So how do I create a 3 input AND gate? I take 2 input AND gates, I tie the output of one to the input of the other, and then I have 3 inputs. There we go, there's a 3 input AND gate. So pretty simple. And now I just need to check each of those lines that we discussed before. So now the question is, how exactly am I gonna do that? Well, I know that I want this line to be 1, so I can just drag that down. I know that I want this line to be 1, so that's good. Now I want this line to be 0. So remember, AND gates are going to propagate the signal, or the output will be 1 rather, if both inputs are 1. So I want to get the output to be 1 if this number is 6. So I need each of these lines to be 1 on the input of the AND gate, so that the output of the AND gate is 1 when I have 6. How do I do that? Well, these ones will be 1 when I have the number 6, so that's easy. But this one will be 0 when I have the number 6. So I just need to invert it. So let's just grab an inverter, NOT gate, put that guy in. We'll change it to north, smaller, and I will just plop that guy in, and there we go. So now this checks whether I have the number 6. And I can actually just hook up my LED straight to this. I'm gonna do something else in a minute here, but really this will work. So this basically accomplishes the task that we set out to accomplish. And now if I kind of simulate this, so let's go back to the pointer finger and start incrementing my counter. So you can see the LED's off the whole time, and then as soon as I get to 6, it turns on. If I go to 7, it turns off again, okay? So there we go, it works. So we've essentially accomplished the task. Now I'm gonna add a little bit of unnecessary complexity to this thing because I still want to show you guys how we use multiplexers. So in this case, it's not really necessary to use a multiplexer. I can just attach my LED directly, but I just wanna show how multiplexers work. Okay, so let's go down to plexers and grab a multiplexer. And we're gonna have a 1-bit select bit, and we're gonna have 1-bit data bits. Okay, so very simple mux. All right, so I'm gonna connect my select bit to the output of this AND gate. And what I wanna do is I want the output of this multiplexer to be 1 when the select bit is 1. So how can I do that? Well, I can actually just put a ground signal as one of my possible inputs, and I'll just put a power as the other. So there we go. So now my select bit will choose this ground line when it's 0, and it'll choose this power line when it's 1. So once again, this is sort of unnecessary in this case, but I just want to show you guys how a multiplexer actually works and how you can connect one in Logisim. So this will do the same thing. It's a little extra hardware, a little unnecessary, a little bit of a contrived example, but you get the point. This is how we use multiplexers, and we can see it lights up just like before using that select bit. So that is it. So that is how we do value detection with these circuits. This is how we can build some cool sequential circuits using digital logic. And yeah, if you have any questions, I know this is a lot that we covered today. Please feel free to reach out as always, and I will see you guys on the next one. Thank you.